Welcome viewers, in this video we'll see the details about sequential circuit or finite state machine. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic sequential circuit or finite state machine FSM. The diagram shows the block diagram of sequential circuit or finite state machine FSM. Now we'll see the diagram. So this combinational circuit with memory element. Combinational circuit, we know that it is adder, subtractor, decoder, encoder. These are all combinational circuit. If the input is given, it will give the output. It will not store any data. That is a combinational circuit. Based on the combination logic diagram, it will produce the output. The memory element is connected as a feedback, then is called a sequential circuit. Memory elements are connected to the combinational circuit as a feedback path, right? So this is the input, combinational circuit, output, and memory is connected. So due to that, we have two different outputs are available, two different states. The next state, present state, right? So this output is based on the input as well as present state, right? So it is based on two things. Normally in combinational circuit, output is based on the input only. But due to the memory element, one bit data is stored. So what is the previous output and what is the input, based on that we'll get the next state, right? So the next state is depends upon previously available state as well as the input, right? Now we'll see this. The information stored in the memory element are at any given time defines present state of the sequential circuit. So 1 bit data is stored, that is nothing but a present state. The present state and the external input determines the output and the next state of the sequential circuit, right? So the data at present, what is available is called a present state. This present state and input will decide the next state. Thus, we can specify the sequential circuit by a time sequence of external inputs, internal state and output. That is present state and next state. Right? It is a time sequence of external input and internal state. So that will decide the output. The counters and registers are commonly the example of the sequential circuits. Right? These counters and registers are made up of this sequential circuit. The memory element used in the sequential circuit is a flip-flop. It is nothing a flip-flop, which is capable of storing 1 bit binary data, right? So it will be able to store the 1 bit binary data. The example is counters and register. Now we'll compare the comparison between this sequential circuit and combinational circuit. We'll see the comparison. So this is the first column is the combinational circuit, second column is sequential circuit. In combinational circuit, the output variable or at all times depends upon the combination of the input variable. So the based on the input variable, the output is produced. There is nothing else, right? What is the input we are giving? Accordingly, the output is produced. But in sequential circuit, the output variable depends not only on the present input variable, but they also depends upon the past history of these input variables, right? So here output depends upon input. This is here output not only depends upon the input, what is the previous state of this circuit. That also decides the next output, that is called next state. That is depends upon previous state and inputs, right? Then you see the remaining comparisons. Memory unit is not required. Here we are using not any memory in combinational circuit. That's just a combination of logic gates available that will produce the output based on the input. But here we are using memory. Memory unit is required to store the past history of input variable. 1 bit data is stored in the sequential circuit. Combinational circuit are faster in speed because the delay between the input and output due to the propagation, this combination faster because the delay between the input and output is due to propagation delay of the gates. Only propagation delays will be there. Then it is the input is given, immediately it will give the output. But the sequential circuits are slower than the combinational circuit because it should verify the earlier, what is the earlier output, so that it is having slower. Easy to design, harder to design, because we need to check what is the present state, next state, storage element, all are available. Here this parallel adder. This example is serial adder. Serial adder depends upon the previous state, right? So these registers, counters, all are coming under flip-flop. Parallel adder, this subtractor, adder, count, then decoder, encoder, all are coming under combinational circuit. Now we'll see the definition of the flip-flop. So the sequential circuit is mostly is nothing but a flip-flop. Now we'll see what is meant by flip-flop. In electronics, a flip-flop or latch is a circuit has two stable states and can be used to store state information. Two stable state means present state, next state. Flip-flop and latches are used as data storage element. 1 bit data can be stored. A flip-flop stores single bit binary, that is binary digit of data. One of it has two states, represent 1 or otherwise represent 0, right? It will store either 0 or 1 as a storage element. So a flip-flop is having two state, present state and next state. It is capable of storing 1 bit data. So in this video we discuss the sequential circuit. What is meant by sequential circuit? That is combination of combinational circuit with memory is a sequential circuit. Then we'll compare the sequential circuit and combinational circuit. We discuss the definition of flip-flop also. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers, in this video we'll see the details about SR flip-flop. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic SR flip-flop. We know that flip-flop is the storage element. The output is depends upon the input as well as previous state of the output. Previous state of output and the input will decide the output. Now we'll see this SR flip-flop. The SR flip-flop, also known as a SR latch, can be considered as the one of the most basic sequential logic circuit possible. So the SR flip-flop is the very basic type of sequential circuit. This simple flip-flop is basically a 1-bit memory bistable device. So it will be able to store the 1-bit data. What is bistable? Has two inputs. One is which is set, that SR refers set reset, right? One is set, that is mean memory. The meaning is the output is 1. Set means it will set the output as 1 and it is labeled as S. S means set, that is output is 1. And another which will reset the device. The meaning is 0, labeled as R, right? So we have they have the bistable device. Bistable means two stages. Set means it will make the output as 1. Reset means it will make the output as 0. So this S refers set, output 1. R refers reset, output is 0. Right? So we can set or reset the output of this circuit. Right? Set means 1, reset means 0. Then the SR description stand for set reset. The set input reset the flip-flop back to the original state with another output Q that will be either at the logical 1 or 0. Depends upon his set or reset condition. Right? Whatever may be the earlier data, 0 or 1, set means it will make the output as 1, reset means it will make the output as 0. Now we'll see the diagram of the SR flip-flop. So the two types available, positive edge and negative edge. Positive edge means whenever the clock pulse rises, the circuit will executed, the output will be executed. Negative pulse means whenever the clock pulse this goes down, goes to 0, it will execute it. So here now we'll see the positive edge. Whenever the clock pulse increases, whenever the clock pulse become the high level, then the circuit will execute. So we have 4 AND gates available, 4 NAND gates. 4 NAND gates are available. This is 1, 2, 3, 4. In 3 and 4, the gate non-gate 3, the S input is given, set input. In NAND gate 4, OR input is given, reset. This positive edge detector clock pulse is given to both 3 and 4. We know that sequential circuit, for every clock pulse applied, the output is executed. The status changes from one state to another state when the application of the clock pulse. That's why it is called a sequential circuit. The combinational circuit, if you give the input, it will give the output. That is why small propagation delay. But the sequential circuit sequentially executes. Sequentially means every clock pulse, the state is changes. By sequence of order, the output is varied. Right. So in NAND gate 3, S input and clock pulse. NAND gate 4, OR input and clock pulse. Right. So the output of this NAND gate 3 is connected to the NAND gate 1. 4 is connected to NAND gate 2. Right. This NAND gate 1 get this output bar, complement of the output Q bar is connected. In second NAND gate, the output is connected, Q is connected. Right. So here we have S bar and Q bar, here R bar and Q. So this is the present state, Q bar. Output complement of the output. Right. Now we'll see, I will go to the truth table, what will happen if the input is applied, what are the possible outputs are available. We'll go to the truth table. I will see some description, then we'll go to the table. The circuit is similar to SR latch except enable signal is replaced by the clock pulse. Latch means we have enable signal, but here replaced by the clock pulse, followed by the positive edge detector circuit. The edge detector circuit is a differentiator. So it is used for clock pulse. The diagram shows input and output waveform for the positive edge triggered clock pulse. We'll see that waveform later. The circuit outputs respond to the S and R inputs only at the positive edges of the clock pulse. At any other instant of time, the SR flip-flop will not respond to the changes in the input. So whenever the clock pulse goes to the positive edge, the output is produced. Now we'll go to the truth table and basic block diagram. So this is the logical diagram. S input, R input, clock pulse, output, complement of the output. CP means clock pulse. Right. This is the truth table. This is very important. The set already we discussed. Set means 1. Reset means 0. We are resetting the output as 0. So this is the clock pulse. This is the positive edge. Going upward means clock positive edge. Going down means negative edge. Right. So here it is going upward. So every clock pulse, the output is executed. So we already know that this is the two inputs, S, R. This is the present state and next state, Qn bar. So this next state, Qn bar is Qn plus 1, not bar. Qn plus 1 is depends upon Qn and two inputs, SR. So Qn plus 1, next state depends upon present state and two inputs. Right. So the two inputs, two variable, 4 combinations are available. 0, 0, 0, 1, 1, 0, 1, 1. Right. So in this Qn is the one variable, 2 possibilities are available. 0 or 1. 0, 0, 0 or 0, 0, 1. 0, 1, 0 or 0, 1, 1. Right. So S and R 2 variable, 4 combination. Q 1 variable, 2 combination. 0, 1. Right. So 0, 0. If present state is 0, what will happen? 0, 0. If present state is 1, what will happen? So there are now 8 combinations. S, R, Q, and combinedly we have 8 combination. Right, now we'll see that. If both S and R is 0, what will happen? No change. present state and next state no change. What is the present state? Same thing will be available as the next state. There is no change in the state. 0 is 0, 1 means 1, right? If both the inputs S and R is yes, set and reset is 0, if the present state is 0 means next state also 0, present state is 1 means next state also 1. No change. This is called no change. Suppose 0, 1. 0 means set is 0, reset is 1. Right. We already know that what is reset. Reset means 0. So whatever may be the present state, next state will be reset. 0. 0 means 0, 1 means 0. Right. It will reset the output. Whatever may be the present state. The output is, the next state is 0. Right. If the reset input is 1, reset means 0. So it will make the next state as 0. If already 0 means same state will be maintained. 1 means it will make it it will reset the output as 0. Then third combination 1 0. What is 1? This is set. Set is 1, reset is 0. So what is meant by set? Set means 1. So it will reset, it will set the output as 1. 0 means it will set the output 1. If already 1 is available, that will be maintained, right? So the set input is 1, the output is set as 1. If the reset input is 1, the output is reset as 0. Right? If both are 1, set and reset, it is an intermediate. It's not defined in the SR flip-flop. That is defined in JK flip-flop. One more topic available is available in the JK flip-flop, but in SR flip-flop, not defined. If the clock pulse is 0, whatever may be the input, 0 in present state 0 means next state also 0. Present state 1 means next state also 1. No change. Right? If the clock pulse, whenever the clock pulse is applied, then only it will execute. Otherwise, there is no change in the output. Right? So we have 0 0. Both are 0 0 means no change. Set 1 means the output is set to 1. Reset is 1 means the output is reset to 0. Reset means 0, set means 1. If both are 1 means intermediate, not defined in SR flip-flop, that is defined in the JK flip-flop. The clock pulse is not available means no change in the input. Right. This is the truth table. From that we can go for the excitation table. That is a very important excitation table. Right. We will see what is excitation table. Is the output. From output we need to decide the input. So this present state, next state. S and R, two inputs. For example, present state is 0, next state is also 0 means what is the input we need to apply. Present state is 0, next state is 1. What is the input we need to apply? 1 to 0, what is the input we need to apply? 1 to 1, what is the input need to apply, right? From output, we are checking the input, right? First we will see 0, 0. Input is also, present state is also 0, next state is also 0 mean what is the input we need to apply. Now we'll check this truth table. Wherever we have 0, 0, here 0, 0 is there. Here also 0, 0 is there. Present state and next state 0. No other. Only these two combination. This first and third. What is the input here? 0, 0. Here 0, 1. That is S is 0. But R may be 0 or 1. So that 0x. Right? See this. Present state is 0. Next state also 0. That can be decided from this truth table. We need to check. For which combination we have present state is 0 and next state also 0. There are two combinations. This first and third. First and third there is no change. 0, 0 is maintained. Present state 0, next state 0. What is the input here? For this first combination 0, 0. S is 0, R is 0. Third combination, third output, S is 0, R is 1. So in both the cases S are 0. Only R may be 0 or 1. Right? So S equal to 0, R is any case, will get 0, 0 as the output. So S is 0, but R may be any value, X, that is represented as X. Then we'll see 0, 1. Present state is 0, next state is 1 mean what is the input. See where it is, we have 0, 1, this is 0, 0. Here we have 0, 1 is there. Only 1. All no other thing. Only 0, 1. Present state is 0. Next state become 1. What is the corresponding input? 1, 0. S is 1. R is 0. 1, 0. Only one combination. Then 1, 0. Present state is 1. Next state become 0. Where it is available? Is available here. 1, 0. Right? Though no other thing. No other combination. What is the corresponding input? 0, 1. Set is 0. Reset is 1. Set is 0. Reset is 1. Then 1, 1. Present state and next state is 1, 1. We have to check. Here is available. 1, 1. Here one more. 1, 1 is there. Two combinations. Second, 2, 3, 4, 5, 6. Then second output and second combination and sixth combination we have 1, 1. What is the corresponding input? 0, 0. S is 0, R is 0. Here what is the corresponding? S is 1, R is 0. Right? Here 0, 0, 1, 0. That is R is 0, here also 0, here also 0. But S is here 0, here 1. So S may be any value X and R is 0. So this is the excitation table. From the output we are checking what is the input. Right? So 0, 0 mean if we give S equal to 0 or any value mean present state and next state will be 0. 0 to 1. If you want to change the present state 0, next state to be 1 mean you should give S input is 1, R input is 0. If you want to change the present state 1 to 0, the input what we need to give? S is 0, R is 1. We want to maintain present state also 1, next state also 1 mean whatever may be the S input, R should be 0. Then we'll get this output. Right? So the excitation table we got from the truth table. From the output we are deciding the input, that is called the excitation table. Right. Now we'll see the truth table in a shorter form. 0, 0 means this is next state, this is present state. Next state and present state both are equal. 1, 0 means set. Set means it is set the output as 1. 0, 1 reset. Reset means 0. Both are 1 means no change. There is not defined in JK flip-flop, SR flip-flop. It will be decided in JK flip-flop. Right? Both are 0. Same. Present state and next state are equal. 1, 0 means set. 0, 1 means reset. Right. Now we'll see some more detail and clock circuit. So the case 1, if S and R both are equal to 0, the clock pulse is applied, the output do not change, there is no change. Next state is equal to present state. Case 2, if S equal to 0, R equal to 1, then output pulse is applied, the next state is 0. R means reset, so the output is reset to 0. If S equal to 1 and R equal to 0, the clock pulse is applied, the state of the flip-flop is undefined. Is not undefined. The state of the flip-flop is 1. Q n plus 1 is 1. Right? If S equal to 1 means set. If both are 1, that is undefined. Right? Now we'll see this clock pulse. So this is a positive edge triggering clock pulse. Whenever the clock pulse increases, rising, this is called a negative edge, down, going down. This is going up. So whenever clock pulse going to positive, this is called positive edge, increasing. This is called negative edge, going down. Here from 0 to 1, positive edge. 1 to 0 is the negative edge. So whenever the clock pulse increases, there is a change in the state of the flip-flop. Right? So S and R both are 0 means no change. S equal to 1 means set. Set means output is 1. Next state is 1. Then 0, 1. Reset is 1 means the output will be resetted to 0. If both are 1 means undefined. So in this video we discussed the SR flip-flop, basic block diagram, truth table, excitation table and the clock pulse. Now we'll verify one of the input. Now we'll check how the states are changes. Now consider this fourth combination. S is 0, R is 1. What happened? The present state 1 is changed to next state of 0. 1 to 0. Right? So S is 0, R is 1. Present state is 0, that will change to present state is 1, that will change to 0. Now we'll verify this output with the logic diagram. See, S is 0, R is 1. And another input is positive clock pulse. Whenever the clock pulse applied, then only it will work, right? So S is 0, R is 1, clock pulse is 1, 1. Then present state, what we discussed, 1. That should changes to 0, right? 1 to 0. We'll verify whether this 1 is changed to 0. Q is 1 means Q bar will be 0, right? Now we'll check this. 0 and 1. What is the NAND gate output? 0 and 1 means 0. Because of NAND gate, it become 1. 0 into 1 is 0 in AND gate. In NAND gate, it is complemented. This is 1. 1 into 1 is 1. But due to NAND gate, it become 0. Right? So this output of this third NAND gate is 1. Fourth NAND gate is 0. Now we'll see here. This 1 is applied here. So Q is applied. Q is 1. Q bar is applied here. That is Q bar is, this Q bar is 0. Q bar is 1, is given as 1. So here the S bar is 1, R bar is 0. This 1 is applied here. From down to up we need to go, right? Presently it is 0. Now changed to 1. That one only applied. We need to follow the logic either from bottom flip-flop to top or top to bottom. Now we'll follow from bottom to top, right? So 1, here also 1. First we'll see this, then we'll go to the flip-flop 2, NAND gate 1. So see here, the output is 0. This Q is applied here. So 0 into 1 is 0. Due to NAND gate, it become 1. Now the Q bar is 1. This 1 will be applied here. This 1 into 1 is 1. But due to NAND gate, it become 0. Now it is changed to 0. Right? We have to follow from bottom to top. Because both are interconnected, we don't know what will happen. Both will be executed simultaneously. In order to study, in order to go with the theoretical, we follow from bottom NAND gate to top NAND gate. Some other combination we have to follow top AND gate to bottom NAND gate, right? There is some procedure is available. There are 8 combination. 4 combination we have to follow from bottom to top. 4 combination we have to follow from top to bottom, right? So I will explain again. Here S is 0, clock pulse is 1, R is 1, clock pulse is 1. We have Q is 1, that should be changed to 0. We need to check whether the Q is changed to 0. Q1 means Q bar is 0. So 0 into 1 is 1, 0 into 1 is 0, but due to NAND gate we got 1. 1 into 1 is 1, due to NAND gate it become 0. Now this 1 is applied. 1 into 0, 0, but due to NAND gate we got 1. This 1 is applied here. 1 into 1 is 1, due to NAND gate it become 0. See this, the output is changed from 1 to 0. Similarly, we can verify the other output or other combinations also. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we'll see the negative edge triggered SR flip-flop. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, negative edge triggered SR flip-flop. We know that SR flip-flop is set reset. Set reset, very basic type of flip-flop. Now we'll see what is the edge, negative edge triggered. In the negative edge triggered SR flip-flop, the negative edge of detector circuit is used and circuit output respond at the negative edge of the clock pulse. Right? So it will respond for the negative edge. Now we'll see what is the negative edge. Let us consider this clock pulse is changing from 0 to 1. It's a rising. This is called a positive edge clock pulse. Changing from 0 to 1. Whenever changing from 0 to 1, this rising edge going upward direction, upper arrow. This is the positive edge trigger. Positive edge triggered clock pulse. See this clock pulse changing from 1 to 0, going down. Changing from 1 to 0, going down arrow. So this is nothing but a negative edge triggered flip-flop, right? So whenever It changes from 0 to 1 during the rising edge, that is called positive edge. That's called a positive edge triggered clock pulse. That flip flop will respond for positive edge during this edge. This negative edge means changing from 1 to 0. Whenever it goes down to 1 to 0, it will respond. That circuit will respond. So that is called a negative edge triggered flip flop, right? 0 to 1 positive edge, 1 to 0 negative edge, going upward, going downward. Now we'll see the logic symbol and the truth table. So this is the SR flip flop. So the clock pulse given is inverted because we are going to apply 0. So for the 0 it should respond mean it is applied in the inverted. When the 0 is applied, it become 1. So it will respond. The logic circuit will respond. Positive edge triggered flip flop, the video available separately available. Previous video is the positive edge triggered SR flip flop. Right. So this is the S input, R input, output, complement of the output, output Q, complement of the output Q bar. So the SR is nothing but set, reset. Now we'll see the truth table. So what will happen in the output? So this is the clock pulse going down. If it is going up means positive edge. This is going down is a negative edge. Right. So there are for SR, 2 inputs, set, reset, 2 inputs. There the 4 possibilities. 0, 0, 0, 1, 1, 0, 1, 1. Then this is the present state, next state. Q1 is the present state of output. Qn plus 1 is the next state of output. We know that flip-flop is the storage device. It will store 1 bit of data. So the output is depends upon input as well as what is the previous output. So this is the previous output and input. So this Qn plus 1 depends upon previous output Qn as well as the 2 input SR. So it's totally 3. These 2 inputs and present state will decide the next state. Right. So 0, 0, here 2 possibilities, 0, 1. Q1 may be 0 or 1. So 0, 0, 0, 0, 0, 1. Similarly, all are 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. In all cases, we have 0, 1. Q1 may be 0, Q1 may be 1. So S or Q1, 3 variables. So 8 possibilities. 2 to the power 3, 8 possibilities. Now we'll see the output. What is the next state? If S is 0 and R equal to R also 0, both are 0 mean no change. Present state stays 0 mean next state also 0. Present state 1 mean next state also 1. There is no change. What is the present state? Same thing will be reflected as a next state. Next state. Right. 0, 1. What is this? 1 is nothing but reset. What is reset? Reset means 0. Right. It will reset the output to 0. Whether 0 means 0, 1 means it will reset to 0. Whatever may be the in previous state, the next state is reset. Right. So 0, 1. The R is 1 and S is 0 means it is a reset state. It will reset the next state of output as 0, 0. Right. 0 means 0 will be maintained. 1 means it will change to 0. Then the third combination 1, 0. What is this 1? 1 is nothing but set. Set means 1. The output will be set as 1. Reset means 0. Set means 1. 0 means it will change to 1. 1 means that same thing will be retained. Right. So 1, 0 means set. The output is set as 1. 1, 1. Both are 1, 1 means is not defined. Is intermediate. This is not this combination is not defined in the SR flip flop. That is available in the JK flip flop. The condition is fulfilled in the JK flip flop. Right. So S and R both are 0, 0, no change. 0, 1 means reset. Their output is reset to 0. 1, 0 means set. The output is set to 1. 1, 1 means there is no change. This intermediate is not defined in this SR flip flop. That is defined in the JK flip flop. So in this video we discussed the negative edge of SR flip flop, logic symbol and truth table. In positive edge triggered flip flop available previous video, in that more details are available. The circuit detail, excitation table, truth table, logic symbol, verification of output. All details available in the previous video. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we'll see the details about JK flip-flop. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic JK flip-flop. We know that flip-flop is the storage element. It will store 1 bit of data. The previous title is the SR flip-flop, set reset. That videos are available separately. So the improved version of SR is the JK flip-flop. Now we'll see the detail. The uncertainty in the state of an SR flip-flop when S equal to R equal to 1 can be eliminated by converting into JK flip-flop. In SR flip-flop, both S and R, the S value and R value is 1, that is not defined. It is uncertain. The output is not defined. So that can be eliminated in the JK flip-flop. How it is eliminated, how the modification in the circuit is, the data inputs are J and K, which are AND means AND gate, with Q and Q bar respectively. That is K and Q is connected in AND gate. J and Q is connected in AND gate. K and Q bar is connected in AND gate. That output is given as a S. S equal to J into Q bar and R equal to K into Q. Now we'll see the diagram. At the time we are able to understand. So the simple thing is J and K is connected in AND gate with Q and Q bar. So that SR flip-flop is converted into JK flip-flop. Now we'll go to the logic diagram. So this is a SR flip-flop. The S input, R input and clock pulse. The output Q and complement of the output Q. This SR flip-flop is converted into JK flip-flop by having two AND gates. In first AND gate, one input is J, another input is Q bar. J and Q bar is connected. The output of this AND gate is the S input, J into Q bar. One more AND gate, the input is K, another input is Q, right? K into Q is the R input, right? SR flip-flop is connected with two more AND gates. The S input is J and J multiplied by Q bar. R input is K into Q. So that it will be converted into SR flip-flop converted into JK. Now we'll see the logic diagram. So there are 4 NAND gates available. That is the basic diagram of the SR flip-flop. 4 NAND gates are there. The output of this NAND gate is connected here, and one more input to this NAND gate is Q bar. The output of this NAND gate is connected here. One more input is Q. So it is interconnected. In this we are giving S and R input, and one input is clock pulse. This S is nothing but J into Q bar. This Q bar. This R input is nothing but K into Q. One input is K, another input is Q. What we discussed earlier, right? J into Q bar. J and Q bar is given to AND gate. That output is given as a S to the one of the NAND gate. K and Q is given to the AND gate. That output is given to another NAND gate. Then these two NAND gates are interconnected. Now we'll verify the one output. We will see later. Now we'll go to the truth table and excitation table. Then we will verify one of the input. I will go to the truth table. So this is the two inputs J and K. 4 combinations 0 0 0 1 1 0 1 1. We know that the flip-flop, the output 2 stages available. Present state, next state. Present state is Qn, next state is Qn plus 1. Because flip-flop is the storage element. So the output next stage is depends upon input as well as previous state. Normally the output is depends upon input only in combinational circuit. Here output is next stage, new stage is depends upon input as well as what is available earlier, previous state also, right? So these three will divide the next state, J, K as well as Qn, previous state. Right. So that first we have 4 combinations 0, 0, 0, 1, 1, 0, 1, 1. In all the cases, we have Qn equal to 0. Then we'll have Q1 equal to 1. Again, we'll repeat. Right. So 2 variable 4 combination. In that, first we'll keep Qn equal to 0. Then same 4 combination will keep Q1 equal to 1. Previous state is 1. So what will happen? Both are 0, 0 means no change. Previous output is 0 means next output also 0. 0, 1, K mean it is called a reset. Reset means 0. Whatever may be the previous state, 0 means 0 maintain, 1 means it will be maintained to 0. So that is available. Reset 0, 1. If Q1 previous state is 1, it will reset to 0. Right? So 0, 1 means the output next state will be 0. Reset. 0 means 0 maintain, 1 means that will change to 0. Then 1, 0. 1, 0 means set. It will set means 1. Set the output means 1. Now the 0 is changed to 1. Here already 1 is there, so same thing will be maintained. Right? So 0, 1 means reset 0. 1, 0 means set 1. If both are 1, then it is toggle. It will toggle. 0 means 1, 1 means 0. Right? So very easy. Both are 0, no change. Both are 1, toggle. 0 means 1, 1 means 0. 0, 1 means reset. The output will be 0. 1, 0 means set. The output will be 1. So that is simplified is given here. 0, 0 means the next state is previous state. Both are same. No change. 1, 1 means the next state is complement of the previous state. Qn bar. 0 means 1, 1 means 0. 0, 1 means set. Reset 0. 1, 0 means set 1. Right. Now this is a simplified truth table is given. No change, reset, set, toggle. Now we'll see the excitation table. What is excitation table? The output is, from the output we need to decide the input. Present state is 0, next state is also 0 means what is the input we need to give. Present state is 0, next state is 1 means what is the input we need to give. So that is the excitation table, because we need in some cases in the while designing the circuit we need to maintain present state is 1 and next state is also 1. What is the input we need to give? Now we'll verify this. 0, 0. Present state also 0, next state also 0. Refer this truth table. So here both are 0. Any other condition there? Here also both are 0. There is no other condition, only this first and second. In that case J is 0. In both the case J is 0, but K is 0 here 1. So K may be X, may be 0, but J may be always 0. J is always 0. K may be anything X. So if you give J equal to 0, K may be 0 or 1, the same thing will be maintained. Then 0, 1. We'll check whether it changed to 0, 1 here. Changed to 0, 1. Only this case. For that, what is the input? 1, 0. 0, 1. What is the any more 0 to 1. So here also one more is there. 0, 1. Right? No, not that. 0 to, so the Qn is 0, Qn plus 1 is 0. 1. 0, 1 we need to refer. So this is 0 to 1. Only this case. Only this case is available. Any other case is there? 0, 1. 0, 1 to 1. Right. So now it is clear. 0 to 1, 0 to 1, 2 cases available. This is 0, this is 1, this is 0, 1. So these two combinations. In that J is 1, K is 0. In the second J is 1, K is 1. So J is always 1 for both the case. J is 1. K may be 0 or 1. So it is X. Right. Qn is 0, Qn plus is 1. These two cases. Changes from 0 to 1, 0 to 1. For this, these two inputs. J is always 1, K may be X. Right. Then 1, 0. So these two cases. 1, 0. This is changed from 1 to 0. This is 1 to 0. Right. This one and this one. So for that case it is 0 1. Here 1 1. So k is always 1. In both the cases k is 1. J may be 0 or 1. So that's x. Then 1 1. Where it is 1 1 is available? Here 1 1, this case. Here also 1 1. Right? This one and this one. Here both are 0. Here 1 0. That is k is 0 in both the cases. K is 0. J may be 0 or 1. So that is x. Right? I think you are able to understand. I will explain once again the first case. Qn equal to 0, Qn plus 1 is 0. What is the input? So first two is the same. Q1 0, Q1 plus is 1. That is these two things are available. In these two things we have to verify the input. Both J is 0 in both the case. So it is 0. But K may be 0 or 1. So it is given as X. Like that we identify all four combinations. This is called a excitation table. Right? Truth table means output. From input we are checking the output. Excitation table means by output, for the given output we are checking what is the input. Now we'll go to the logical symbol and characteristics equation. So this is the logic symbol. Earlier we discussed S and R, S R flip flop. From that we constructed JK. So this is the total JK flip flop. J and K, two inputs, clock pulse, output and complement of the output. From the excitation table Qn and JK, we can see by using K map we can identify Qn plus 1 from the truth table. This is from the truth table, right? So what is the output? Qn plus 1 equal to Qn bar J plus Qn into K bar. So this is the characteristics equation of the JK flip flop. This K map is constructed using the truth table. By using the truth table, here Qn one input, J and K another two inputs. We know that Qn plus 1 depends upon previous output and two inputs. So that we are having Qn and JK three inputs. From that we calculated next output Qn plus 1, next state. So this is the equation. Now we'll see the clock pulse. So the clock pulse, this is called a positive edge triggered. Whenever changes from 0 to 1, the process will be executed. So this is the K value and this is the J value and K value. Right, what we discussed in the truth table. So this is reset, toggle, no change, set, toggle and toggle. Just keep on changing. It is purely based on what we discussed in the truth table. So in this video we discussed the JK flip flop, how it differ from SR flip flop. The disadvantage of SR flip flop is eliminated by JK flip flop by connecting two AND gates. Then we discussed the truth table, excitation table, logic symbol, characteristics equation and clock pulse. Now we'll see one more. We'll verify one of the output with the logic diagram. Let us consider this combination. J is 1, K is 0. Present state is 0. That should be changed to 1. Right? J1, K0. The 0 should be changed to 1. Now we'll check with this logic diagram. J is 1, K is 0. The output is 0. It should be changed to 1. We have checked whether this present state 0, the next state changed to 1. For this combination J equal to 1 and K equal to 0. Right. So the J1, what is the one more output is nothing but Q bar. Q bar is 1. Q0 means Q bar is 1. So here we get 1. K equal to 0, one more input is Q. Q is a 0. So here both are 0. 0 0 means output will be 0. 1 1 means output will be 1. One more input is clock pulse. So here both are 1. Here 0 1. Right. 1 into 1 means 1. But here NOT gate. AND gate means 1. NAND gate means 0. 0 1 means 0 in AND gate. NAND gate means 1. Right. Now we got 0 here, 1 here. Right. Now we'll see this. So this Q bar is connected here. Q bar is 1. 1 is connected. 0 into 1 means 0 in AND gate. NAND gate means it is 1. Right? See this, now 0 is converted into 1. Now apply this 1 here. Here both are 1. 1 into 1 means 1, but NAND gate means it is 0. Right? You have to follow from top to bottom. So both are interconnected. We don't know how it will execute, but we have to follow certain procedure. You have to follow the top AND gate first. From change of output, that output is applied to the bottom NAND gate. Right? From some 4 combination, we have to follow the top. Another 4 combination, we have to follow the bottom. First we have to find the bottom output. That output will be applied to top NAND gate. Right? So from the truth table we can decide. There are 8 combinations available. 4 combination we have to consider output from the top NAND gate. Then that will be applied to bottom. Or next 4 combination, it is reversed. Right? So now we'll verify the output also. For j equal to 1, k equal to 0, the state changes from 0 to 1. We verified with the entire logic diagram. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we'll see the details about D flip-flop. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, D flip-flop. We know that flip-flop is a storage element. It can store 1 bit of data. The output, we have 2 stages, present state and next state. So the next state output depends upon present state as well as input. So the input and present state of output will decide the next state of output. So this is the basic about the flip-flop. In this we will see the D type of flip-flop. The basic building block of D flip-flop is the SR flip-flop. From SR flip-flop we are developing the D flip-flop. The SR flip-flop have 2 data input, S and R. Normally it is set reset. S refers set and R refers reset. The S input is made high to store 1 in the flip-flop, and R input made to high to store 0 in the flip-flop. If S is high, then we can store 1. If R is high, we can store 0. That is the basic about the SR flip-flop. When both the inputs are same, the output either does not change or it is invalid. So that is the disadvantage of the SR flip-flop. If S and R both are same, either 0, either 1, 1. S equal to 1 and R equal to 1 means it is a invalid. That is, it is not change. Input 0, 0 means no change. Input 1, 1 means invalid. That is the case. So in order to avoid this, we can go for the D flip-flop. Now we'll see the logic diagram, how the D flip-flop is developed from the SR flip-flop. Right. So this is the SR flip-flop. 4 NAND gates are available. Right. So for this NAND gate, the S input is given. The second NAND gate, R input is given. These 2 NAND gates are interconnected. The output of first is connected to third NAND gate. Output of second NAND gate is connected to fourth NAND gate. And this is the output, Q bar. Q and Q bar is interconnected. Q is connected to fourth NAND gate. Q bar is connected to third NAND gate. So this is the basic block of SR flip-flop. In this, only one input is given. The D flip-flop, only one. D input is given to S. Inversion of D input is given to the R flip-flop. Right? So the S and R inputs are inverted. S0 means R1. S1 means R is 0. S0 means R equal to 1. So both are inverted. So this case will not arise. 0, 0 or 1, 1. Right? S0 means R1. S1 means R0. So this case will not arise. No change and invalid case will not arise. Either 0, 1 or 1, 0. These 2 inputs. Right? So the D input is given to S. The D is inverted. That is given to R. Right? So that we can get that S and R may be 0, 1 or 1, 0. 1, 1 and 0, 0 will not arise. So these sample inputs we'll see later. Now we'll see the further details, truth table and excitation table. Then we'll see the sample example, how the input and outputs are changed. So this is the basic symbol, S and R, SR flip-flop, output and complement of output. D input is given to S, inverted D input is given to R. So S and R will be always inverted. This is the clock pulse. So this diagram can be simplified as D input, only one input, Q1 Q bar is the output, clock pulse. So this is the basic diagram, this is the revised diagram, simplified diagram. Now we'll see the further description and truth table. In many applications, these input conditions are not required. That is 0, 0 or 1, 1 is not required. Either we need 0, 1 or 1, 0. These input conditions can be avoided by making them complement of each other. This modification of SR flip-flop is known as D flip-flop. Right? Then SR flip-flop, we modified that S will get the input, inverted input will be get by R. So 0 means 1, 1 means 0. The D input goes directly to the S input and its complement is applied to the R input. Due to this condition, only two conditions exist. That is either S equal to 0 or equal to 1, or S equal to 1 or equal to 0. Only these two conditions available. That no change and invalid condition 0, 0, 1, 1 will not occur. Now we'll see the truth table followed by the excitation table. So this is the truth table. Before that we'll see this. So this is the input, D input. This is present state. This is next state. We already told the next state is depends upon present state and input, because this is a storage element. Always one input, one output is available. So while giving the input, the output is depends upon earlier available output as well as the present as well as the input. Right. So in this D flip-flop, the nature is whatever may be the present state. The next state is nothing but D input. D equal to 0 means next state also 0. D 0 means 0. 1 means 1. Right. So the D input will be reflected in the next state. It will not bother about present state. So D and Qn, 2 bits, so that 4 combinations are there, either 0, 0, 0, 1, 1, 0, 1, 1. Right. The output depends upon previous state and input, 2 digits available, 4 combination. On all 4 combination, what is the thing means? What is the D value that is available as a Qn value, next state. D0 means 0, 1 means 1. It will not bother about the present state. That is the nature of the D flip-flop. So that is given here. D0 means Qn plus 1 also 0. D1 means Q1 plus also 1. X. So whatever may be Qn, earlier stage. So this is invalid. Right? 0 means 0, 1 means 1. That is the nature of T flip-flop. It's a D flip-flop. Right. Now we'll go to the excitation table. What is excitation table? From the output, from output we decide the input. For example, present state is 0, next state is also 0 means what is the input we need to give? That is the excitation table. Input is identified from the output. 0, 0 means what is the state. 0, 1 means what we required. 1, 0 means what we required. 1, 1 means what we required. So it is already very simple. We already discussed that D and Qn plus both are same. D will be reflected as Qn plus 1. Right. So the Qn plus 1 value is the D value. Right. Whatever may be the present state. Qn plus 0 means we need D as 0. Reversed. Here D 0 means Qn plus 1 is 0. Qn plus 1 0 we need means D should be 0. Qn plus 1 means we need 1. So here 2 digits of 4 combination. 0, 0, 0, 1, 1, 0, 1, 1. Right. So for this 0 and 0, present state is 0 and next state also 0 means the D input is this one, this Qn plus 1, 0. Present state is 0, next state should be 1 means the D input is 1. That is nothing but Qn plus 1. Present state is 1, it should be changed to 0 means the D input is 0, this value. Present state also 1, next state also 1 means D value should be 1, right? It is very simple. Now this is reflected here. What we discuss in the truth table, D will be reflected in Qn plus 1. Qn plus 1, if you want this value mean the D should be Qn plus 1. So both are same, right? So this is the excitation table. From the output we are deciding what is the input required. For this state, what is the input? That is called excitation table. Suppose if you want to change 1 to 0, then we need 0, right? Now we'll see the one example. We will verify with the logical diagram. We'll take this input. D is 1. Qn is 0. Present state is 0. Qn plus 1 should be 1. Changed from 0 to 1, right? D input is 1. Output is 0. That should be changed to 1. Now we'll verify with the logical diagram. So the D input is 1. Q output is 0. It should be changed to 1. We'll check whether it is changed to 1. Right, here 1 is given. So the S input is 1. The 1 is inverted. So this is nothing but inverter. NAND gate, same input is given. It acts as a NOT gate. So here we'll get 0. S equal to 1, R equal to 0. That is the advantage of the D flip-flop. And clock pulse is given. That is 1, 1. So here in this first NAND gate, both inputs are 1. 1 means output will be 1, but due to NAND gate it is 0. AND gate means 1, NAND gate means 0. So here we got 0. Here 1, 0. 1, 0 means 0. AND gate means, NAND gate means 1. Right. So here we got 1. Right. Now we'll see here, this 1 is applied to here. Applied to the third NAND gate. We'll go from top to bottom. Right. This 1. Q equal to 0 means Q bar will be 1. This 1 is applied. So here 0, 1. 0, 1 means 0, but NAND gate, it be 1. Right. 0, 1. The output of NAND gate is 1. See this now, 0 is changed to 1. Now this 1 is applied to the fourth NAND gate. So here 1 into 1 means 1, but NAND gate means 0. Right. So the Q bar will be 0. Q equal to 1 means Q bar will be 0. Right. So we verified that if D equal to 1, the present state 0 changed to 1. Step by step we verified. Right. We have to follow from top NAND gate to bottom NAND gate. Some procedure is available. Both are interconnected. We don't know which one will be executed. Either this or that. But we are following the certain procedure. We have to follow from top. First we have to identify the output of this third NAND gate, then followed by the fourth NAND gate. So in this video we discuss of the D flip-flop. Details about D flip-flop. That is, it is constructed from SR flip-flop with the inverted input, so that we can avoid 0, 0 input and 1, 1 input. We discuss the logic diagram, logical symbol, truth table and excitation table. That is output. From output we are deciding the input is called excitation table. And we verified the one set of input also. D equal to 1 means the output changes from 0 to 1. That also we verified. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we'll see the details about T flip-flop. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. T flip-flop. We know that flip-flop is the storage element. It will store 1 bit of data. The output we have 2 stages available, present state and next state. So the next state output is depends upon present state as well as the input. So the output is depends upon earlier available output as well as the input. So this is about the basic of flip-flop. Now we'll go to the T flip-flop. T flip-flop is also known as toggle flip-flop. Output is toggled. This T flip-flop is modification of JK flip-flop. That is, T flip-flop is obtained from a JK flip-flop by connecting the both inputs J and K together. J and K get the same input. That is nothing but T flip-flop. If we give the same input to J and K inputs, that is the T flip-flop. Now we'll see the logic diagram of the T flip-flop. So this is the JK flip-flop. J, 1, 2, 3, 4 NAND gates are available. This first NAND gate J input, second NAND gate K input, then it is interconnected. So in this we are giving the same input, this is a T input, only one input is given to J as well as K. J and K getting the same input. One more input is clock pulse. We know that it's a sequential circuit. Every clock pulse the stages will changes. And one more input for this NAND gate 1 got from the Q bar. Q bar is also one of the input. For second NAND gate is the Q. Q is the one of the input. Right. So the first NAND gate got T input as J as a T input, clock pulse and Q bar. Second NAND gate gets same T input as a K input. Then clock pulse, then Q. Right. So this output of first NAND gate is connected to third, second NAND gate is connected to fourth. This third NAND gate, one more input is Q bar. Fourth NAND gate, one more input is Q, that is interconnected. So that we got Q as the output, Q bar is the complement of the output. So this is the basic logic diagram of the T flip-flop. J and K getting same input. For one sample output, we will verify the output, whether it is changes, how it is changes. After the truth table, we will verify this. I will see the description and truth table, then we will verify one sample input. So this is the logic symbol, JK flip-flop, output and complement of output and clock pulse, same input is given. T as the input given for J as well as K. This logic symbol can be modified as single input J and complement of output and complement of output and clock pulse. So this is a real symbol, this is a modified having one input. Then we will see the truth table and excitation table. So the truth table, this is the T input, this is the present state, this one is next state, Qn T Qn plus 1. We already know that the next state of output is depends upon the input as well as earlier available output Qn, right? Qn plus 1 is depends upon Qn and input. So Qn and T, two variables, 2 digits, so 4 combinations available, 0 0 0 1 1 0 1 1, right? So the T equal to 0 means there is no change. What is the present state? That will be the next state. T equal to 1 means present state 0 means that will be toggle, 0 become 1. If T equal to 1, the present state will be toggle, 0 means it become 1. Again T equal to 0 means present state is 1 means next state also 1, no change, 0 means no change. Again if T equal to 1 means present state is 1 means it will change to 0, right? So T equal to 0 means no change. T equal to 1 means 0 become 1, 1 become 0, right? So the same truth table written in another manner, T Qn plus 1. This Qn plus 1 depends upon Qn and T. 2 variable, 4 combination. 0 0 0 1. This T is 0 means no change. T is 1 means 0 means 1, 1 means 0, toggle. So here it is very clear, T is 0 means no change, 0 means 0, 1 means 1. T equal to 1 means toggle, 0, present state 0 means next state 1, present state 1 means next state 0, right? So both are same, it is written in a different manner. Now from that we can go for the characteristics equation. So this is the modified. T0 means Qn plus 1 is Qn, both are same. T1 means Qn plus 1 is Qn bar, toggle. 0 means 1, 1 means 0. Say T0 Qn, T1 means Qn bar. Now from this we can go for a K map. Qn is the one input, t is the another input. From that we can find qn plus 1. Here 0, 1, 1, 0 is there. So it is 0, 1, 1, 0. So not possible to combine. Both are available individually. So the characteristic equation is qn plus 1 equal to t qn bar plus t bar qn. So characteristics equation. Now we'll see the excitation table. What is excitation table? The present state and next state. From that we need to identify what is the input. Truth table means from input we are checking what is the output. Now output, for this output what is the input required, that is called excitation table. For example, present state also 0, next state also 0 means what is the input, what is the value of t. Present state is 0, next state is 1 means what is the value of t we need to give. That is called the excitation table. So qn plus 1, 2 bits. So 4 combination 0, 0, 0, 1, 1, 0, 1, 1. We'll check the first one. Present state is 0, next state is also. From here we'll check. See, this is the present state is 0, next state is also 0. And what is the input? 0. We need to give t as 0. If it is 0, 1, present state is 0, next state is 1. Here it is available. Present state is 0, next state is 1 means the t value is 1. Then 1, 0, it is available here. Present state is 1, next state is 0 means the t should be 1. Both are 1. That is available here. Q1 is also 1, Qn plus also 1. For that, the t input is 0. Right? So for this 4 combination, we decided t. Suppose if you want to maintain, you want to change, present state is 1, next state should be 0 means the input what we need to give is 1. That is called excitation table, right? I will explain again. 0, 0 means t is 0. 0, 0 means t is 0. 1, 1 means also t is 0. 1, 1 means also t is 0. 0, 1 means t is 1. 0, 1 means t is 1. 1, 0 means 1, 0. 1, 0 also t is 1. Right? Okay. Now we'll check the one of the input. One sample input will verify. We'll take this. The t input is 0. Input is 0. Output is 1. The same 1 should be maintained. Right? Input 0. Present state is 1. Next state also should be 1. Now we'll check this with the logical diagram. So in this logical diagram, input is 0. Output is 1. The same 1 should be maintained. Now we'll check. If q is 1 means q bar will be 0. Right? T is 0. Q is 1. Q bar is 0. So the same 0 is given to NAND gate 1 as well as NAND gate 2 as a J, K inputs. One more input is clock pulse. Both are 1. This NAND gate get Q bar as a one of the input. Q bar is 0. So 0, 0, 1. This NAND gate get Q as a input. So this 1. Q is 1. So it got 1, 0, 1. Right? So 0, 0, 1 means the answer is 0 for AND gate. NAND gate means it is 1. Similarly here 1, 0, 1 means 0, but NAND gate it will give 1. Right? So the output of first NAND gate is 1, second NAND gate is also 1. Now this third NAND gate get Q bar as a one of the input. Q bar is 0. Right. Now we'll follow from top to bottom. We have to follow certain procedure. Both are interconnected. We don't know which one will be executed first. But we need to consider first we'll execute 3, then we'll go for 4. We have to follow the certain procedure for theoretical understanding. Right. So the third NAND gate get 1 as one of the input, 0 is another input. 1 into 0 means 0. Because of NAND gate it is 1. See, the same 1 is maintained. Now this 1 is applied here. 1 into 1 means 1. NAND gate means 0. Right? So the same stage is maintained for t equal to 0. Right? Q is 1. After executing, the Q is also same. 1 is maintained here also. Right? We already know that t is 0 means no change in the output. Present state and next state is same. That is what we discussed. If t equal to 1, the present state next state will change. 0 means 1, 1 means 0. So in this we discussed about the T flip-flop, that is the modification of JK flip-flop having same input to J and K. We discussed logical diagram, logical symbol, truth table, then excitation table. Excitation table means output. For the given output we are checking what is the input required. Then we verified one of the input also. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the race around condition available in the flip-flop. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, race around condition in the flip-flop. We know that flip-flop is the storage element. It can able to store 1 bit data. The output is depends upon the earlierly available output as well as input. The input and present state of output will decide the next state of output. That is the basic of the flip-flop. So in this, what is the race around condition? It is the phenomenon which occurs in level triggering JK flip-flop when there is a 1 at both the input terminals. For example, in JK flip-flop, the J value as well as K value is 1. Both are 1. In that case, the race around condition is exists. What is that race around condition? Race around means continuous toggling. The output will toggle from 0 to 1, 1 to 0. It is continuously toggle. Why it is toggling? If the width of clock pulse is too long, because we know that flip-flop, every clock pulse the status will changes. It is a sequential circuit. When the clock pulse applies, the state will change from one state to another state. So in this, the width of the clock pulse is too long compared to the propagation delay of the gate. The state of flip-flop will keep on changing. That is from 0 to 1, 1 to 0, 0 to 1 and so on. And at the end of the clock pulse, its state will be uncertain. We don't know what is the output, right? So the clock pulse is too long, but propagation delay of the gate is lesser. So the state is changes from 0 to 1. But still, after changing also the clock pulse is there means it will keep on changing 0 to 1, 1 to 0. Right. So that we need to maintain clock pulse is less than the propagation delay of the gate. That is the one thing. Another thing is we can go for master slave flip-flop. That is two flip-flops are connected in series. So that is the remedy for this race around condition. So the clock pulse is more, propagation delay is less, the race around condition exists, that is 0 to 1, 1 to 0 changes. So the clock pulse duration less than or equal to propagation delay of the NAND gate. So that is TP, clock pulse should be less than DT, that is the propagation delay of the NAND gate. So this is possible in edge triggered flip-flop. Edge trigger means during positive edge or negative edge, that is from 0 to 1. When the clock pulse changes from 0 to 1 is a positive edge triggering. 1 to 0 is a negative edge triggering. That is one possibility. Another possibility is master slave flip-flop. Right? So these two cases available. By using master slave or edge trigger, we can avoid this race around condition. So in this video we discuss race around condition in the flip-flop. Welcome viewers. In this video we will see the race around condition available in the flip-flop. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, race around condition in the flip-flop. We know that flip-flop is the storage element. It can able to store 1 bit data. The output is depends upon the earlierly available output as well as input. The input and present state of output will decide the next state of output. That is the basic of the flip-flop. So in this, what is the race around condition? It is the phenomenon which occurs in level triggering JK flip-flop when there is a 1 at both the input terminals. For example, in JK flip-flop, the J value as well as K value is 1. Both are 1. In that case, the race around condition is exists. What is that race around condition? Race around means continuous toggling. The output will toggle from 0 to 1, 1 to 0. It is continuously toggle. Why it is toggling? If the width of clock pulse is too long, because in the we know that flip flop every clock pulse the status will changes. It is a sequential circuit. When the clock pulse applies, the state will change from one state to another state. So in this, the width of the clock pulse is too long compared to the propagation delay of the gate. The state of flip flop will keep on changing. That is from 0 to 1, 1 to 0, 0 to 1, and so on. And at the end of the clock pulse, its state will be uncertain. We don't know what is the output, right? So the clock pulse is too long, but propagation delay of the gate is lesser. So the state is changes from 0 to 1, but still after changing also the clock pulse is there, means it will keep on changing 0 to 1, 1 to 0, right? So that we need to maintain clock pulse is less than the propagation delay of the gate. That is the one thing. Another thing is we can go for master slave flip flop. That is, two flip flops are connected in series. So that is the remedy for this race around condition. So the clock pulse is more, propagation delay is less, the race around condition exists, that is 0 to 1, 1 to 0 changes. So the clock pulse duration less than or equal to propagation delay of the NAND gate. So that is TP, clock pulse should be less than DT, that is the propagation delay of the NAND gate. So this is possible in edge triggered flip flop. Edge trigger means during positive edge or negative edge, that is from 0 to 1. When the clock pulse changes from 0 to 1 is a positive edge triggering. 1 to 0 is a negative edge triggering. That is one possibility. Another possibility is master slave flip flop, right? So these two cases available. By using master slave or edge trigger, we can avoid this race around condition. So in this video we discuss race around condition in the flip flop. Now we'll see the master slave SR flip flop. SR flip flop, master slave condition. A master slave flip flop is constructed from two flip flops. One circuit acts as a master and another acts as a slave. Then overall circuit is referred as master slave flip flop. The diagram is shown below. So this is the master slave SR flip flop. This is one SR flip flop. This is second SR flip flop. First one is act as master, second one is act as the slave. The clock pulse is given to the first flip flop. Inverted clock pulse is given to the second flip flop. So that the race around condition 1 does not exist between master and slave. That is our main objective. To avoid the race around only, we are adding this master slave flip flop. Two flip flops are connected in series with the inverted clock pulse. Now we'll see the condition of the clock pulse. So this is the clock pulse available. Clock pulse is the S and R. Right. This keep on changing. This is the master output. So see this master set, slave set, master reset, slave reset, master no condition, slave no condition. Like that it will keep on changes. There is it will not occur both S and R will be 1. That is the race around condition. It consists of master flip flop and slave flip flop and a inverter. Both the flip flops are positive level triggered, but inverter connected at the clock pulse of the slave. So the master will get the clock pulse directly, slave will get the clock pulse through the inverter. These flip flops are forced it to trigger at the negative level. Negative level is triggered. The output state of the master flip flop is determined by the S and R input at the positive clock pulse, right? So the master flip-flop is triggered at positive clock pulse. The output state of the master is then transferred as an input to the slave flip-flop. The master output is given to the slave. The slave flip-flop uses this input at the negative clock pulse to determine its output, right? So the master flip-flop is triggered at positive clock pulse. Slave, then master output is given to the slave. The slave is triggered at the negative clock pulse. Now we'll see what is meant by positive edge and negative edge. See, this is the clock pulse. So this is 0, 1 and 0. So this is the positive edge from 0 to 1. Changes from 0 to 1. This is a rising edge or positive triggered. Then what is negative triggered? This one. 0, 1, 0. And changes from 1 to 0. Here 0 to 1. Changes from 0 to 1. Rising. Here 1 to 0. Still it is 1 only, but is a negative trickling. Falling edge. Right? So every falling edge the slave is triggered. Every rising edge positive master is triggered. So the master flip-flop is triggered at positive edge. Slave flip-flop is triggered at negative edge. This is called positive triggered and negative triggered. Right? 0 to 1. This is 1 to 0. Then what is the status of the flip-flop? SR flip-flop. This is the two inputs and present state, next state. What are the four conditions? If both the inputs are 0, then the output, the present state is 0 means next state also 0. If the both are 0, present state is 1 means next state also 1. There is no change for 0, 0. Right. Then 0, 1. 0, 1 means reset. Reset means it is reset to 0. Then 1, 0. 1, 0 means set. Set means 1. The output will be set to 1. If it is 1, 1, it is undetermined. Right. So the 1, 1 is undetermined. That is applicable in the JK flip-flop. This fourth condition is determined in the JK flip-flop. Right. Both are 0 means no change. And R input is 1 means reset. Reset means 0. S input is 1 means set. Set means 1. Both are 1 means not defined. That is available in the JK flip-flop. So in this video we discussed what is meant by race around condition in flip-flop, followed by master slave SR flip-flop. Two SR flip-flops are connected in series. Then clock pulse is given to first flip-flop, that is master. Inverted clock pulse is given to slave. So that master SR flip-flop is triggered positive edge. Slave is triggered at negative edge. And also we discussed the truth table of the SR flip-flop. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the race around condition available in the flip-flop. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, race around condition in the flip-flop. We know that flip-flop is the storage element. It can able to store 1-bit data. The output depends upon the earlierly available output as well as input. The input and present state of output will decide the next state of output. That is the basic of the flip-flop. So in this, what is the race around condition? It is the phenomenon which occurs in level triggering JK flip-flop when there is a 1 at both the input terminals. For example, in JK flip-flop, the J value as well as K value is 1. Both are 1. In that case, the race around condition exists. What is that race around condition? Race around means continuous toggling. The output will toggle from 0 to 1, 1 to 0. It is continuously toggled. Why it is toggling? If the width of clock pulse is too long, because we know that flip-flop, every clock pulse the status will changes. It is a sequential circuit. When the clock pulse applies, the state will change from one state to another state. So in this, the width of the clock pulse is too long compared to the propagation delay of the gate. The state of flip-flop will keep on changing. That is from 0 to 1, 1 to 0, 0 to 1 and so on. And at the end of the clock pulse, its state will be uncertain. We don't know what is the output, right? So the clock pulse is too long, but propagation delay of the gate is lesser. So the state is changes from 0 to 1, but still after changing also the clock pulse is there, means it will keep on changing 0 to 1, 1 to 0, right? So that we need to maintain clock pulse is less than the propagation delay of the gate. That is the one thing. Another thing is we can go for master slave flip flop. That is, two flip flops are connected in series. So that is the remedy for this race around condition. So the clock pulse is more, propagation delay is less, the race around condition exists, that is 0 to 1, 1 to 0 changes. So the clock pulse duration less than or equal to propagation delay of the NAND gate. So that is TP, clock pulse should be less than DT, that is the propagation delay of the NAND gate. So this is possible in edge triggered flip flop. Edge trigger means during positive edge or negative edge, that is from 0 to 1. When the clock pulse changes from 0 to 1 is a positive edge triggering, 1 to 0 is a negative edge triggering. That is one possibility. Another possibility is master slave flip flop, right? So these two cases available. By using master slave or edge trigger, we can avoid this race around condition. So in this video we discuss race around condition in the flip flop. Now we'll see the master slave JK flip flop. The diagram shows the master slave JK flip flop. Positive clock pulse applied to the first flip flop, that is called master, and inverted clock pulse is applied to the second flip flop, that is called slave. Now we'll see the diagram, logic diagram of the master slave JK flip flop. So this is the flip flop 1, 4 NAND gates are available. This is another flip flop, another 4 NAND gates are available. This is slave, this one is master. Both are connected in series. Clock pulse given to the first flip flop, master. Then that same clock pulse is connected through the NOT gate, is given to. So the inverted clock pulse is given to the second flip flop, slave. So it is nothing but positive edge is triggered by the first flip flop, because of inverted negative edge triggered by the slave flip flop, second flip flop. Then here the preset is available. We can preset. Similarly here clear is available. So the main objective of this master slave flip flop is the race around condition can be eliminated. If both inputs are 1, J is 1 and K is also 1, mean the toggling will occur continuously. That can be avoided by connecting two flip flop in series with inverted clock pulse. Now we'll see the description one by one. When clock pulse equal to 1, the first flip flop is enabled and the output of QM and QM bar respond to the input of J and K according to the table. So the clock pulse is 1 mean only the first flip flop will be enabled, because second flip flop getting inverted. So the clock pulse becomes 0 for second flip flop. Only first flip flop is enabled. So based on the truth table, the value of J and K, the output present state and inverted present state will be available. At this time, the second flip flop is inhibited because of its clock pulse is 0. CK is 0. Now we'll see the truth table. What is the truth table of the JK flip flop? When the clock pulse is applied to the first flip flop, what will happen? So this is the two inputs J and K. This is present state and this is next state. Qn is present state, Qn plus 1 next state. We know that flip flop is a storage element. It will store 1 bit data. The output is depends upon input as well as earlierly available output. So this output next state is depends upon what is the present state output as well as the input j and k. So qn plus 1 depends upon j, k two inputs and previously available output qn. Now we'll see the combination. If both are 0, if both are j0 and k0 means what is the present state? Same thing will be reflected. 0 means 0, 1 means 1 if both are 0. Present state and next state is same. There is no change. So that is also given here. jk qn plus 1. J also 0, q also 0 means qn plus 1 is nothing but qn. Next state is previous state. Right. Next one 0, 1. J is 0, k is 1. Actually it is SR, reset. Reset means, if reset input is 1. Reset means what is the reset means 0. If the previous state is 0 means next state also 0. If previous state is 1 means next state is 0. It is reset. The output become 0. Whatever may be. If it is 0 or 1, the output become 0. The next state becomes 0. For the case 0, 1. 0, 1. 0 means 0. 1 means also 0. Then 1, 0. 1, 0 means j input is 1. That is set. It will set the output. Set means 1. 0 means 1. 1 means 1. Whatever may be the input, the output is 1. It will set. That is given here. 0, 1 means the output will be 0. 1, 0 means the output will be 1. Next state will be 1. Suppose if it is 1, 1. Both are 1, 1. Means toggle. 0 means present previous state is 0 means next state will be 1. Previous state is 1 means next state will be 0. That is qn bar. So this is the truth table of the flip-flop. Both inputs are 0 means there is no change in the next state. Both are same. qn plus 1 equal to qn. 0, 1 means the next state is 0. Reset. 1, 0 means the next state is 1. Set. 1, 1 means toggle. qn bar. Now we'll see the remaining description. When clock pulse goes low, ch bar equal to 1, the first flip-flop is inhibited and second flip-flop is enabled. At this time, the output of second flip-flop follows the output qm and qn bar respectively. That is the, if ch, the clock pulse is low mean first flip-flop is disabled, second flip-flop is enabled. Output from first flip-flop is applied to the second flip-flop. Second flip-flop got the input from first flip-flop, that is given. Since the second flip-flop follow the first one, it is referred to as the slave and the first is referred as master. Right? So the second one is termed as slave, first one is termed as master. Right. In master slave JK flip-flop, state changes occurs when flip-flop goes through both positive transition, first half of the clock, and negative transition of the clock, second half. Right? So during positive transition, the first flip-flop will work. During negative transition, second flip-flop work. Thus, race around condition does not exist in the master slave flip-flop. So the race around condition means both the inputs are 1. That is not possible here because of master slave. Master got positive edge, slave got negative edge. So the race around condition is eliminated in the JK flip-flop. Master slave JK flip-flop. So in this video we discuss about what is the race around condition in the flip-flop, how to avoid. One method is master slave, and we discuss about master slave JK flip-flop. Master and slave, two flip-flop connected in series. Master is the first flip-flop, got the positive edge clock pulse. Second flip-flop, slave got inverted clock pulse, negative edge clock pulse. Then we discuss the truth table of the JK flip-flop, and we discuss how to avoid the race around condition. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.